So hello everybody and welcome to another video today about a relatively new topic, which is the agentic AI topic. So everybody heard probably right now that agents are everywhere and what things are going on here, and what I want to talk a bit about is how you can use this, in your scientific workflows, how as a bioinformatician you can use this, how as a how should I say it, as a data scientist you can use this in your workflows, and not only as a coder basically, and basically extend this to all other kinds of use cases. So what you need to know basically is what are these agents. So these agents, they are semi-autonomous machines, as I write it here, that run on top of an LLM. So it's kind of a loop which runs on top of an LLM, and basically what it does, it gives you interaction with other devices or with other things than just you talking to the LLM. Yeah. So you're outside the prompt. Yeah. So you can read, write files, of course, on your drive, on your local machine. You can use so-called tools. So tools, what is this? Basically, it's programs that are running on your computer. And it allows you, of course, to interact with your computer. And as you can just basically call programs on your computer, well, it allows you also to interact kind of with the physical world, because if this program has consequences in the physical world, or it controls some kind of robot which is connected to your computer, then the LLM can basically work with it. Yeah, this is the main idea. And in the end, it's a nice user interface where you can just talk to someone and basically your computer does the action. Yeah? That's the whole story behind the agents. What does this look like? So we have here a little setup, what we want to do basically. So we have an agent. This agent has to be connected to some kind of LLM server. This LLM server, it might run locally on your network, on your computer. Again, it can be somewhere in the cloud, on the internet. The agent in general, it runs on your computer, or can also run in the cloud, but basically if you want to have it interacting with your computer, well, you want to have it interacting with your local computer probably, or of course wherever you run this. And it can interact, as I said, well, with the operating system, with the data, with the programs that are basically on this computer. So it's also a trust issue, because you have to trust the agent what to do on your computer. Not go into all the details. This is a quick separate video about how you can run things. Yeah. So what I want to do basically in this video is I want to show you basically how you can set this all up, how you can get things like this running, and what this small context protocol is. Yeah? So the small context protocol is basically, it allows you to build these interfaces between the agent and your local system. Yeah, this is kind of the whole idea behind it, and we will show you quickly how you can do this and how things work. Yeah. What is the software that we use? So basically, you already heard about the Llama.cpp engine in previous videos about the RAG and things like this. So basically, it's an engine that allows you to run large language models on commodity hardware on your machine if you want it. For this use case, you better have a GPU, because the contexts are getting rather large. Yeah. We will run this Qwen 3.6 model, which is a rather small model, but it's kind of the model where things start to work. It's one of the first models that you kind of can use. 35 billion parameters that you can use for this kind of agents. Yeah, so don't go with 7 or 8 billion parameter models. There are people who say they are successful with this, but you will suffer. Go with models, start with the Qwen 3.6 model, and if it doesn't work for you, go to a higher model. Of course, you also need the hardware to run this. I can't help you with that. You can run the Qwen 3.6 model on a CPU. If you have a rather decent CPU, you will get an output of like around 10 to 20 tokens a second if you configure it right. That's just enough to do what we're doing here, but it will be rather slow. Yeah? So you better get the GPU somewhere in order to get things running. You have to connect these things to an agent. So the agent is basically this tool here. We will run the crush. Yeah? So we will use this tool here from Charmbracelet, which is called Crush. I use it because basically it comes in one binary. It's a compiled program. It's not some kind of scripting stuff that's made up from Python or from JavaScript. It's written in Go. It's compiled on your system. You can download this on this website here from the Crush website. Yeah? I will show you how to configure the agent, basically how to configure the agent so that it works with your local tools, how you can build tools and how you can get these tools basically to run with the agent. And I will show you basically how to write custom tools for the agent. So what does this mean, tools? Yeah, as I said, basically it's how to write the interface between the agent and what's running on your local system. Yeah, you have to define these interfaces. The Crush agent comes with a lot of interfaces. It can already browse the web. It can already read and write to files on your system, use a shell command. But of course, you want to do it special stuff. Yeah, and I will show you how you can achieve this. Okay, so we will go into this. In order to write these things, we will use the model context protocol. For the model context protocol, there's like a Python library which will help us to write these model context protocol servers. So basically, you have to run local servers with tools which build kind of these interfaces to your local machine. I mean, the agent also runs on your machine, maybe the LLM even runs on your machine, but they still have to talk somehow to the programs underlying in the operating systems. And there's a library in Python, which is the MCP library. If we go here, it's called the MCP SDK. If my browser comes up, it's not sure about that, but basically that's what we have here. Yeah. Basically this, so here we are in this PyPy project. It's a bit slow here. It's called the MCP Python SDK. We will use this in order to build our MCPs. The MCP is basically this interface. You see, it's the model context protocol. It allows you basically to interface your computer with the agent. Basically you have here a website which comes from Anthropic, basically, which started this whole MCP story. How it works. Yeah? We will show it to you here. And then in the end, I will show you a bit how to apply this to bioinformatics and to science. Because the story is like, what you should know is these LLMs are inherently language-based. And the problem is that science is often not language expressed or not in a language expressed as English in which we talk. Yeah? So science is often expressed through math. You could say it's a language, but mathematical reasoning is not the strengths of language-based models. Yeah? Numerics, graphs, so basically numerics, if you get the column of numbers out of and you say this is my result, and you plot a graph out of it, the LLM will not really be able to work with it. So you have to kind of translate this into natural language for the LLM to understand, okay, I run this tool gives me a certain result. Let's translate this tool back and into language, and then the language it understands, and it understands, okay, I was successful, the experiment, it worked, we got this result, but you have to describe it, as I said, in language. Yeah, it does not work, this is the result, and you get back, I don't know, a matrix of thousands by thousands of values, because first of all you overload the context window, and second, the LLM will not reason about this. Yeah, so these programs, these interfaces, they have to work in language. Okay, so it's you who asks in language the agent to do something, and the agent launches basically a program on your machine. The machine generates some result, but this result has back to be translated back into language. Otherwise, it does not work. This is fundamental. Yeah. If you build MCPs, and of course, they are not allowed to exploit the token window. So you could say, okay, this is my result, and you give them 100 numbers back. But in the end, this will first of all exploit the context window, and the LLM will not know what to do with it. Yeah. This is the basic problem that we have here. So we welcome to the practical. Let's go into practice what this looks like. Yeah. So I will show you first a little agent. So we have here installed on this machine the Crush. And in order to run the Crush, of course, I have to set it up with an LLM. So I will quickly go into the configuration. So basically, how is the Crush configured? So locally, you can configure it basically for all configuration. You can basically put it in your .config directory, like so, and then it kind of is configured for all the directories. If you have some kind of project that you use this tool with, you can just create a Crush JSON file in the folder of the project, and it will read this JSON file for this project. Yeah. Okay, so what we have here basically is, this is basically my setup here. So what does my setup look like? So basically I say, okay, the schema, so this is basically the line that you always have to build in, because basically it's kind of the default settings that this Crush uses and the schema that it will use. And then basically we have to tell him, look, these are basically our large language providers, and later when we build the MCP, I will also show you how to put into this Crush JSON file basically your MCP. Yeah? What do we have here? So this is very easy. So this here is like a default provider for everything that Llama.cpp hosts. Yeah? And I give it basically the base URL. So this is basically the machine where it runs. This is the OpenAI chat endpoint that it automatically generates. So how we will set this up? So I have here a couple of machines. I have a machine here in our lab with an A40. On this A40 we will run our model. So the A40 is a GPU, for those who don't know. And the machine basically runs on this IP address, and I will basically just SSH into it and forward the port here locally to my machine so that we can use it with the Charm Crush. Yeah? So if I do this, basically, first what we do is, so it runs on port 8080, so I forward the port 8080 from this machine to my local machine, so that also the whole communication is encrypted. So if you run things locally and you have your own server on the network, you can do things like this. We go to this IP address, and basically then we get access to this stuff. Yeah. Otherwise, you could just run Llama.cpp locally, as I've shown you in another video. I hope that my password works. So we connect it to this machine. This at localhost is basically this machine over there where this runs. There's kind of a tmax session, I guess. Maybe not. Let's see, tmax attach. Yes, and here basically we have Llama.cpp running. Just to show you what this does, so basically we have the Llama server. Basically this is the model. We use this Qwen 3.6 35A3 parameter model. This is just from the way I downloaded it. The file name is still like this. I tell it, okay, host it on all IP addresses, basically that this machine is available. This NGL means put all the layers onto the GPU. So there's a CUDA system here, just show this off, where we have an A40 with 46 megabytes of VRAM, where we comfortably can run this model in 8-bit quantization, that we've downloaded from Hugging Face. So you find these models on the Hugging Face website. You take the GTUF file if you run this in Llama.cpp like here. Here we already have compiled Llama.cpp. I guess you can go to the Llama.cpp website to find out how to set this up, how to get Llama.cpp working on your local system. Okay, I run this here. So this is basically the model. It loads the model into the GPU. Right now the model is running. And just to check it out, basically this is the normal inference endpoint. If my browser starts up, and if I go right now into localhost 8080, then what we basically have is we have here basically this website for Llama.cpp, and I could ask questions here, and this is just the typical chat front end that this Llama server provides, but the Llama server provides also the OpenAI endpoint. Yeah? So how are you? If I do this, I very quickly get an answer. It's reasoning a bit, and she says, I'm doing well, how are you today, and blah blah blah, what can I help you with? Yeah. So this is basically the story. What it does. But as I said, we use this with the Crush, and I will show you how to put these MCP servers into the Crush and how to work with it. Context window, I always put it here. As we said here, basically you can name these models and give them an ID. It does not matter for what we're doing here. What's important is the context window, because basically there's like a summarization phase in these models. And the context window, basically, I guess it's like 200,000 for this thing, but keep it smaller. I honestly keep it like at 80,000 something, because sometimes when you get data back or something like this, not that you overshoot the context window, because then basically the Crush, it stops and you can't kind of really recover your session very easy from the point where you have been, if your context has been overshoot. So keep this smaller, because sometimes it overshoots because a result from the MCP comes back, and basically your context window overshoots. Okay. So let's, as we set up everything, let's start up the Crush. This is the coding agent. As I said, you find this on this Charmbracelet Crush website that was before in the slides. I will also put it down in the video description. It asks you to initialize your code base, as this is a coding agent. For what I'm doing right now, I don't need to initialize my code base. Yeah. So just to show off what this does, as I said, it can connect to these MCP servers to interact with my machine. So far we have none here. We have skills here, basically, that I also that this thing basically where I can describe how this tool can do certain things. Yeah. That's not so important. You can also include language servers so that it can reason better about code, as this is a coding agent. But already, as this is an agent, basically it can do a lot of things. So basically, just to show you some example what this tool can, it's like find me good restaurants in Vienna. Do a web search, and actually this is really cool, because basically normally if you use the tool just with Llama.cpp, actually it can't do a web search, yeah, but as this here can use local tools, it kind of can do things like this, yeah. Basically the LLM starts and you see basically it wants to fetch, it wants to make a search and basically check this thing out there. So basically I can say right now allow this for this session in order to make web searches. It gets something back, probably that it may not be allowed to do it, but basically it parses then the contents, and it kind of works for you as an agent using these tools in order to give you a result. Yeah. And we see here the nice thing is, as we kind of have locally running the server in the lab, we see here how things work in the background, how it's processing these tokens. Basically it's still an LLM, and you have these back and forward loops about getting things done. Yeah? So basically right now it looks up a lot of websites, and it will tell us basically, okay, well, this is a good restaurant or not. Yeah, you get the idea. I will not maybe run this till the end for our tool, but we already have it. So basically we see what are good restaurants, and I can tell you as a Viennese, okay, I know at least some of these restaurants. that you have here a list of restaurants that you can go to in Vienna that are basically, all of them are rather upscale restaurants, to be honest, most of them, but that's basically the story here, yeah? And you have basically an idea how this works, and of course it found this restaurant on the web, and it did not, basically we have avoided this cut-off problem that we have in LLMs, where basically they don't know about things that newly happen because it really performed the web search in order to do this. So far so good. This is basically what we want to do, okay? Right now, as I said, we have these cut-off problems in LLMs, and this is kind of one of the things that we can address. So the first tool that we can say, that we want to build here is like, add the system time to our things and kind of get the system time and tell me what time is it right now, yeah, without performing a web search, which of course this tool could do, but we want to build this with this MCP tool thing that we want to do, yeah, and then MCP is basically nothing else in this case than a Python script. So how would I go for that? To show this a bit off. So I open here my Emacs, and let's build basically an MCP server. I will call this the time mcp.py. What do I have to do to build an MCP server? You see, it's rather straightforward. It's really just a few lines of code. So I will go here, MCP server fast MCP. So basically you have to install this MCP tool. You can do this with pip install MCP as I've shown it to you on this PyP website. It's rather straightforward, yeah. Import, I want to have fast MCP, so basically this is the API that you want to use in order to make everything simple. And we want just basically the agent to allow to have access to our system time. Yeah? So how do I program this? Well, as this is all in Python, we can say from datetime import datetime, and we can say, okay, we want to generate a tool for the agent. So this uses this new add syntax in Python, and then basically you define a function, and the agent can call this function. And of course you have to describe the function, so basically you have to write the docstring what it actually does, and you also have to type, so you have to use right typing. This is very important here, yeah. So what do we do here? So I tell him get current time, and here I have no arguments because it's just getting the current time. Normally I have to use the typing infrastructure from Python in order to put this, so that basically this tool can validate is the input that comes from the LLM right there. The LLM, you know, it hallucinates sometimes. It doesn't do the right things, yeah. So if the input does not work, it cannot call the tool, and so it kind of validates the input, but we will see this, yeah. So we have the current time right now, and we tell it, okay, we have a dictionary that comes back, and we want to have a string dictionary back, because basically we just put one string back, which is the datetime string, yeah. So what does this tool do? We have to describe this to the LLM, so you better write the docstring here, and we say yield the current time. Yes, the current time. Let's not make it complicated, so that we can ask for the current time, and it gives us the time from the machine. Return, and we can say, okay, what to return? Well, the current time. So basically you want always the return format, because most of the models, the LLM models, they're basically trained on this in this JSON format, yeah, in like JSON-like format. So as Python dictionaries are basically almost in this JSON format, it's rather easier. So we kind of return this in this kind of dictionary format. This is a very good idea. And normally what you can do, you can import here any and say from typing import any and basically replace the string with any. Then it's easier for the dictionary to get things back, yeah, to help your things out. But here, as we have a string which comes back a strings, it's easy, yeah. So what do we want to have? We say datetime now. Okay, so we want to have the current datetime. And this is basically our first MCP server. And in order to start this, basically all we have to do is MCP run. Yeah? What I show you here in this video is basically an MCP server which runs using standard I/O output. That's not the only thing that you can do. You can basically build more complicated things that run on the web. And you can also, of course, include MCP servers that are out there on the web. I guess there are whole libraries that basically you can search for them on the web and include them in your agent. But this is the basic idea how to do this. So this is how you build your MCP. And of course, you could query here a database and say, look, is my database entry. Yeah. As I said, you have to make sure that you don't overflow the context window. If you overflow the context window, of course, if you say, okay, I query for the database and I get back 100 results, then you might get into trouble, because if these 100 results all contain, I don't know, 10 entries, then you're already 1,000 results, and you have to parse them, and you don't have to overshoot the context window. So you have to think about it, yeah. So maybe, for instance, you put something, okay, if this is in text anyways, this table that you get back from a database, only get me the first 10 results, yeah. That's basically it, yeah. So this is the structure of an MCP server. That's all you have to do, and here, of course, you can put all that Python provides you and all that you can do, call on your local machine. You can call here programs, you can do whatever you like, basically, yeah. What's important is that here, basically, this goes back in language and that these descriptors are right, yeah. Okay. In order to make this more visible, we will then go into a Chromex example, where we will analyze a trajectory. But this is basically our time MCP right now that we have here in my work directory as home hashka. I need to know this so that I can configure basically our crush JSON. So I will make here a new directory. I will call this with time. And here I have a project where I want to use this time MCP, and so I will copy my default crush config, because I don't want all of them to use this, of course, this config here. I will just, config crush JSON. So basically I can just put the JSON file here, and then it will read by default first the one from here. And we will edit this, and we will basically add the MCP server. So how do I add the MCP server right now into my agent? This is kind of the big idea how to do this. So we need here MCP, this is a JSON file, MCP basically, and we have to tell him, well, what does this MCP? So I will just call it basically, and give it some fancy name, but I will call this here just current time. I guess this is instructive enough for the whole system here. And we have here basically, what does it do? Type. This is basically standard I/O. So as I told you, if you have it running as a web service, you could put here HTTP or whatnot. Here I just want to get you started with these whole things, yeah. Command, basically the command in order to run this MCP server, and as this is a Python file, well, basically we say the command is Python, and then we have some arguments, which is basically the file, yeah. You could all code this up in C, yeah, or some other libraries. I will show you here in Python so that it's really easy for you to get started with this fast MCP. With this fast MCP API that we are using here, if you want to, yeah. And then my MCP server, it's in home hashka test MCP, no? That's basically where it is. Yes, okay. Time MCP it's called. pi. And if I did not make any mistakes typing this, so here I close this one, and then as I continue with the providers, I need a comma here, so that this is a valid JSON. I hope it's fine. I hope I did not make any spelling mistakes. And if I run right now the crush again, we see, okay, we have, it always asks me to initialize this project, but we don't have anything to initialize here. And we have an error, so basically, probably in our Python file we made something wrong. Because we see the MCP is loaded, but it doesn't show up here. I will quickly open that in Emacs and check if I find the error, hopefully very fast. What could go wrong here? I guess I found it already. Let's see, Emacs time MCP pi. So basically, I said here MCP run, but of course we don't even have this MCP tool here, so I forgot here to do this here with fast MCP, and we will call this, what do we call this MCP server? We will call it the clock. Yeah, so this is basically how you get this MCP, then it can do this MCP run, and then the crush can run the whole thing. So this is basically all you need to know. Yeah, this line here, name your MCP server, run it, here the tool, and this is basically the function that your system can call, and this is the result that it can get, and basically it can then reason about, it can use these tools and reason with them. Yeah. So let's do this again. Quit the crush, start the crush. Where's my MCP server? And the MCP server came here. We have our current time, basically one tool. So because in the file that you've seen, I wrote MCP tool with this @ symbol. And if I would have more tools, it would tell me that I have more tools here, basically. And what I can do right now is tell me the current time. And if I do this, basically what it will do, it will understand that it has a tool for that, hopefully. It asks me, can I use this tool? So time get current time, so basically time, because this is what we called this here. And then we have this function, if you remember, when we go in the MCP server here, we called it here, get current time, so it wants to run this function get current time, and it asks me basically if it's allowed to do this, and I can say of course allow, and I get this back, and it tells me the current time is this. Yeah, this is what you want, and you can imagine how performant this is, because if I can hook this up right now to my local databases, I can hook this up to my code bases, to whatever I want, basically, and have it reason about it. Yeah, that's the basic story behind all this. Okay, so far so good. What you can do with this as a scientist, what you can do with this as a biologist, what can you do? You can imagine right now a lot of things, of course, because you have your Python thing. It gives you something back. Basically, you ask it to do these things. And it knows, okay, I have these tools available, I will use these tools in order to get to my result and to give an answer back to my user, basically, my LLM. Yeah? And the nice thing is, right now I have a user interface which is like to all this, where I can just talk with my machine and it does things that happen on my machine. Yeah? That's as easy as it gets, no? I guess you hope you understood basically the power of this right now. So to make you understand the power a bit more about this, I want to show you some other things. We have basically here on my local machine, I have an MCP server somewhere. I hope it's mounted. Yeah, and we have here basically with Chromex And here I have a kind of a fast Chromex MCP. It's not a real Chromex MCP, but I want to walk you over this quickly, that I've written just basically to get Chromex trajectory analysis. Yeah. So basically what we can do here is, where we have to parse an XVG file and whatever, that's not so interesting, but basically what I want to show you is, I don't know if you know Chromex, for instance. Basically it's a molecular dynamics tool, for those who are not familiar, and what we have here, for instance, is, well, one of the easiest things if you have performed such a molecular dynamics simulation, what it does, you have some kind of molecule, and this molecule, well, it deforms over time, no? And during the simulation, and we want to see how much it has deformed over the simulation, and how you do this is called, you calculate this root mean square deviation, yeah? And basically you have a program on your computer that can do this, yeah? So I can do here gmx RMS, and then I have a lot of, options to do this, and say, okay, calculate me this RMSD over time according to my molecular dynamics simulation, yeah? That's basically what you can do here, yeah? The story is, if you do this, you get basically an XY graph, so basically you get a t-axis, where in time, for each step you get an RMSD, and you get a column of numbers, yeah? And what I want to insist on is this, of course, does not work, yeah? You can't put a column of numbers back to your agent, yeah? It will not reason about this, yeah? So you have to translate your things into text, yeah? So how do we do this here with this root mean square deviation? So basically the first thing is we limit the number of samples, yeah? So we tell him, look, tell me the maximum number of samples that you want back, and these trajectories, they're very often, they contain a lot of frames, so a lot of spots that are basically that are saved there, so 50,000, 100,000, so imagine you get 100,000 numbers back, so basically this is already limited to 1,000, and if basically the LLM has the idea to take more than this number of samples, we get it the errors message, and it can call the tool again and kind of understand, look, okay, let's call this with less samples, yeah? This is kind of the idea here. And then the next idea is basically what we have here, of course, so these error messages, and then we call the tool, so this is basically run gmx subprocess, so basically up there's a function. These are basically the arguments that I put here on the command line, and this here basically this calls a command line subprocess which is basically defined like this. This is all straightforward. This is just basically run a process on my system, run a binary that's on my system, yeah? But then I have to interpret the results. Yeah? So let's go back to this root mean square deviation. And the question is, well, as I said, you always have to get this back into language somehow. Of course, it parses then the result. So it gets this XY graph. So it gets the time on the x-axis. It gets the RMSD in nanometers, how much the atoms have deviated from the initial position. Here out, and we then get basically this story here. So what a good idea is, for instance, for a story like this is, of course, I can give him back some values. So what I do here is I tell him, look, that's the maximum, that's the mean, that's the median. Minimum is not really interesting because at the start it's at 0 and it can only grow. But what, for instance, is interesting here, I can make, for instance, a curve fit and can say, look, this RMSD, it could look like this, but it does not look like this. It looks like this. Maybe the curve fit fails. Things like this. You understand? You can't just give back the values, but you have to tell it something like this. So basically what I do here is I do a fit, and the model basically is this. So we have basically an E function, E minus lambda t. So you can imagine basically when this molecule, it evolves in time, and it kind of changes its states, yeah. And at a certain time you get some kind of plateau, yeah. And the story is like, in general, if there's nothing else happening than just this molecule expanding, then this is kind of a law like this. So this is like a E minus lambda t function, which kind of reaches its plateau according to this kind of law here, yeah. And we can just fit this, and in many cases, of course, this will not work because I don't know if it interacts with a ligand or something like this. All of a sudden, we break out of the plateau or whatever, yeah, in this kind of simulation. But this does not matter because in the worst case, I give it, okay, either the fit just doesn't fail, or I give it the error values, and it then can reason, look, this is not the case here, and if it's the case, then it knows what actually happens. Yeah, that's kind of the idea. And so what I do here basically is a summary. I tell him, look, this is the mean, this is the median, this is maximum RSMD, this is the number that was sampled that is basically in the trajectory, and this is the number of samples that you have requested that I give you back, and I kind of downsample this whole story. Yeah. And then it can look, of course, into the numbers, of course, not into many. Yeah. So if this is very huge, of course, it will not work. But I can tell him, look, I fitted this result here. This is the fit. So I can give him here back A, B, the lambda, and the error of this fit. And or of course, if it did not work, well, fit did not work. And I can tell it basically, look, time series is then the number of samples that he has requested, and if it's not much, he can at least reason about the few samples that he has. Yeah. This is an example that I give you here just to understand how you have to retranslate basically your results back to language. Yeah. So you get if you run this RMSD tool, you get a very numerical result, okay? You can plot this numerical result, but basically the LLM will understand nothing. It will not understand the plot. It will not understand the 50,000 values that come back, yeah? So you have to translate them. What I do here in this translation, well, I fit it according to a law. I tell him, look, let's check this out. Relaxation result, I tell him, look, the fit model, basically, this is the law that I've used. This are the values that come back, understand it, and then the LLM can reason about these things, okay? And I tell it basically, look, this is the median RSD, this is the highest RMSD, and it can say, look, for the system that you've used, this is frequent, this is not frequent, these things work, yeah? Just to make your understanding, you have to translate back your results to language in the best case in order to do this. Yeah? If you feed something, tell it, okay, put the trend curve inside. Look, the trend, I don't know, is this one, okay? That's basically how LLMs can reason with you and work with your tools. And basically here I have, of course, multiple tools, and it can run these multiple tools and basically then reason across all these multiple tools. I just wanted to show you basically the root mean square deviation tool with the input and the output that comes basically out of it. And of course there's the Python code in between, which is not so complicated to run this, to understand what you can do with these things. Yeah. And you can use this basically as a bioinformatician in order to orchestrate, to build a system where you can just talk with your computer and tell, look, I have a simulation here, analyze this simulation for me. Yeah, and this is probably what we will do right now. Yeah, I will use this file here, and if we call this here Chromex, this MCP is called Chromex trajectory analysis. And we will kind of use this MCP in order to investigate the Chromex trajectory, yeah? With our Crush tool here. So how will we do this? Again, I've shown you already how to configure the Crush. We will go here back into I will call this here, we have with Chromex, mkdir with Chromex, and I will just copy basically into this with Chromex, into this with Chromex folder my crush JSON from the with time, and just change it, change the MCP server that I want to have. Of course, you could have multiple MCPs that you can use, yeah, so we could have here multiple MCPs in this kind of story here, but the MCP server, of course, right now with the Chromex, we will call it basically molecular dynamics trajectory analyzer, molecular analyzer, something like this. This is standard input output. Where do I have this saved on my machine here? So it's basically here. How can I get this path here out right now? MNT, let's keep it like this, and I will just write it off. Underscore Chromex, and here we have the Chromex MCP. I hope I didn't make any mistake, of course, because otherwise it will not run. We see this here, we have the MCP running, we have a trajectory, and basically I have prepared a little simulation trajectory story here, so that we have this, yeah. So just to check this out, basically we have here, I call this sim mini because I made a very small trajectory so that this runs rather fast, and we can basically visualize this in VMD. So we can go here into conf out go, and then we get this simulation, and we have here our little peptide here in the simulation. So we have this water box, we have here this little peptide, and we want to have kind of the RMSD across this peptide here, and I could of course load right now the trajectory into the molecule. This is kind of the trajectory here. It's just like 1000 frames or something like this, and of course this is not, you see here basically the trajectory, it has periodic boundary conditions, and this is why we have these water molecules here. Let's make this a bit more fancy here. We can stop basically the import here, but what I want to have here is basically representations, and we want to have all not water, then it will help a bit, and we see basically this is our molecule and how this molecule basically behaves here in this little box, in this water box, and due to the periodic boundary conditions, basically with all the molecules that are half in one side of the box and half in the other side of the box, this is why we had these strange lines. Yeah, I increase the thickness here, then you see it better on the video. This is basically this molecular dynamic simulation that we have here. It's a little peptide, and we want to have this little peptide. Basically, we want to have the RMSD of this little peptide, and I can just go here and grow in this tool here in VMD and say, look, I want to have this peptide, and I want to have basically the RMSD of this peptide. Yeah, but I have a better idea. I mean, I have the crush now. And I have the crush which can do this for me with my tools that I built. So the story is like, I can go here, my with Chromex folder, where I have this MCP server configured, and I can say, look, crush. And no, I don't want to initialize the project, so you could basically call this already inside the story here, and we have basically not just one tool, but already 5 tools basically available for this. So we not only have the RMSD, but that I've shown you, but we have different tools in order to basically to analyze the trajectory. And what this allows me basically in writing these kind of tools is that we can do something like this right now. And this is basically the big deal, because you could say, okay, I hook this up to my database, I hook this up to my workflow, and I can basically use LLMs to run my workflow. Yeah. That's the great idea about this. So let's run this, and when I go here, basically I have to find my molecular dynamics trajectory. So it's in H and then mini sim or something like this, sim mini. I should have just gone to this folder and put my cross-JSON there, but that's fine. I can do something like and it can read file on my system, of course, so I can do something like this. I have a simulation in this folder here, and I paste this here into it, and in GROMACS, because these are GROMACS trajectories, and my molecular dynamics, basically I wrote them in these tools that these are GROMACS, this works for GROMACS tools, yeah. Analyze it for me. Okay. I mean, I could say calculate the RSMD for me, and it would do it with the tool that's available, but let's make it a bit more fancy because we have multiple tools, yeah. What it will do, and we'll see, yeah. So basically it asks me, it has this ls tool already, these are built-in tools into the Crush. It wants to read the directory, I say yes, yeah. Of course I could allow him to do all these things automatically, but you see basically right now what does it do. It uses the molecular trajectory analysis, and it creates an index. I guess there's no index right now in this stuff, and in order to use these tools it needs an index. So we have an MCP basically. We can look it up basically in the code here, which is called generate index or something like this. It's an index file for the other tools. So we have basically this GROMACS create index tool, and it understands, look, I need an index in order to run my things. So let's create one. Yeah? And we basically what this index tool does, basically it just calls gmx make index with the structure file, and that's it. Yeah? And it can do this. So it generated me the index. Yeah? And right now, what does it want to do? There's also an index analyzer so that it kind of understands the system. And right now it says, okay, let's run the RSMD, and let's run get me the radius of gyration, and it runs these tools, and this trajectory, it should be rather small, so actually the tool should be rather fast. Of course, if the trajectory is longer, it takes some time, and we get the RSMD result here back, but of course not from him, it's just basically him making these inquiries. Right now he wants to calculate the radius of gyration, and we will see basically what this LLM does just for me, just by writing, look, analyze this trajectory for me. Yeah, that's basically the story here behind that. Yeah. I click here always allow because look, this if you can basically, there's like a YOLO mode, it's called, just to check this out. Yeah. If I type PHP in this here, everything is allowed, but this runs on my local machine. You never know what the LLM really does. You always have to be a bit careful. And we see basically it used some of the tools that are in here, and basically it gives me an interpretation about my molecular dynamics trajectory. Yeah. So we see basically what's the system overview. There are like this number of atoms. I'm not sure if that's right, but probably this is the water molecules. This is the protein backbone. I don't know. It's 143. amino acids. We have, that's a bit strange, oh no, that's the number of atoms, yes, because it's just a little peptide. We have 13 residues because it understood this from the index, basically. And it knows what's going on there. So it understands that this is a water box with 6 counter ions. It tells me, look, this is what happens. This is the RSMD, as I told him. Yeah, okay. He gets these median values. He can calculate basically the story here out, and we see that the R2 score is rather good with our model that we had. So basically, it was an exponential relaxation fit, and basically. Followed by stable but drifting conformation. So basically he can interpret that for me and do all these things with the little function that I've shown you before. Yeah. Okay, we get an interpretation, we get a radius of gyration, we get all these things back because, I mean, of course I programmed a radius of gyration wrapper in my MCP just as I did it with the RSMD stuff here, but you get the idea how to run these things, how this works, and that it's rather easy to set up. Yeah? I mean, you have seen basically the RSMD, the root mean square deviation tool here, and you can program all these kinds of tools for all your workflows that you want to have, and then just use them together with here, as I've shown you, with Crush and with the Crush JSON file. That's what I wanted to show you basically in this video. I guess that's enough for today. Have a good time. See you another time.